Good evening to all. My voice is audible. It is clear. Okay. Shall we start the class? No, sir. Or still wait? Because strength is less. They have joined only 182 people. Hello, Chandra sir. Okay. Okay. So we'll start the class. Okay. So in the previous class, we have started the topic called as micro-programmed control. Okay, we'll be waiting for some more 4 minutes until your friends will join. Then we'll start. Okay. Anyhow, up to then, I'll just revise whatever the previous topic was there. Okay, so previously we have discussed regarding micro-programmed control, the control unit. Okay, what is this control unit? Which generates control signals or which initiates series of micro instructions. Okay, so it will be implemented using two methods. One is hardwired control unit. Second one is micro-programmed control unit. Hardwired control unit, the control signals will be generated using the logic diagram or conventional logic techniques such as encoder, decoder, multiplexer, etc., etc. So using this logic diagrams or the logic circuit diagrams, we will be generating our control signals so that to perform a specific task. Okay, now coming to this micro-programmed control unit, the control unit which uses to generate control signals using software, nothing but using next address generator, then control address register, then control memory, then control data register, from which we will be obtaining a decoding technique. Using the decoder, the bits will be generated or the control signals will be generated. Okay, so in our micro programmed control unit, there will be having two memories. One is main memory, second one is control memory. The main memory will be storing the actual instructions to be executed by the computer and which can be altered if any change in the program is there. Now voice is clear or breaking? ISMA 7F, voice is breaking or clear? Okay. In between it is breaking. Wait for a while. Okay, it's clear. Right. So in your micro program control unit, we will be having two memories. One is main memory, second one is control memory. Main memory consists of actual instruction actual instructions to be executed by the computer, okay, and which can be altered if any change in program is there. Okay, so it can be act as your random access memory. Okay, you can access at any time if you want to change. Whereas control memory, okay, it stores the micro program or the micro instructions, okay, which cannot be altered if any change is there, that are permanently stored. That's why it can also be called as read only memory. Okay, so in this one, uh, okay, where are these micro operations being stored? The micro operations are being stored in micro instructions. Micro instructions are stored in micro program. Micro program is stored in control memory. Control memory is stored in control unit. Control unit is stored in CPU. Okay, so like this, a simple thing is being discussed, right? So now, in the previous class, we have discussed some parameters like routine, subroutine, right? What is this routine? Routine is nothing but a action to be taken. We can call routine as action to be taken. Okay, so every micro instructions are being stored in your control memory in groups called, which can be specified as routine. Okay, now subroutine, these are the programs used by other routines to achieve a particular task. Okay, it can be called from any point within main body of microprogram. For example, calculating the effective address. See, in every micro instruction, there will be some micro operations to be performed to for executing each micro instruction. So we have four things. One is fetching the instruction from memory. Second one is calculating effective address. Third one is executing the instruction. Fourth one is returning to the fetcher. Fetching, calculating, executing, then again return to fetch. So these are the four steps, these are the four micro operations will be performed to for executing a single micro instruction. Okay, so in every micro instruction, if you want to execute, you need to execute these four micro operations, nothing but so the calculate the effective address will be a subroutine. So you should not go each every time this one. So this will be there already in your program. Okay, so when you call to this one, it will automatically goes to subroutine. Okay, so this is about your subroutine. Now coming to the next one is conditional branching. Now voice is clear, ma? Right? No breaking, right? Okay. Conditional branching. See, the name itself, it indicates conditional branching. Branching, nothing but the branch. Okay, where you should go, that is nothing but branching. So conditional, condition applied. If you are a CSEA student, go to the CSEA class. If you are ITA student, go to the class. If no, unconditional. Okay, if no, again increment the next class. Okay, like that it checks whenever it is met or not, the condition will be met or not. If it is yes, then go to your branch, otherwise increment the address. Okay, so that is nothing but your conditional branching. So the conditional branching provides decision making capabilities in the control unit. So there should be some status conditions. The status conditions are what? The status conditions are special bits in the system that provide parameter information. What is this parameter? Such as you can see in your adder circuit, when you are adding two numbers, there will be possible of getting some carry. Okay, so that are your status bits which provide the carry out of a adder circuit. Like that, the sign bit of a number, whether it is a positive or negative. Like that, mode bits of instruction. In which mode the instruction gets instruction type. Nothing but you'll be seeing this one in your second unit of CPU, where we'll be having different modes, different types of instructions. Okay, indirect addressing mode in that one. Okay, so up to here, the status bits is nothing but which provide parameter information such as the carry out of adder, the sign bit of a number, mode bits of instruction. So the information in these bits can be tested. The information in these status bits can be tested and actions initiated based on their condition, whether it may be 1 or 0. If it is 1, true, 0, false. Okay, the status bits together with the field in the micro instruction specifies a branch address. Okay, you want to locate the branch address to which branch I need to go. So for that one, this status bits with the help of field in the micro instruction specifies a branch address. So you can go to that branch address, then control the conditional branch decisions. Understanding, ma? Understanding? We will be having some status bits which are special bits, okay, which provide parameter information. Okay, using these status bits, whatever the information present in that one can be tested and actions initiated based on the conditions. Okay, the status bits together with the field in the micro instruction specifies a branch address, control the conditional branch decisions generated in the branch logic. The branch logic hardware can be implemented in many ways. The branch logic hardware can be implemented in a variety of ways. The simplest way is to test the specified condition. Test the specified condition. If it is met, if it is true, branch to the indicated address. Okay. If test the specified condition. If it is true, branch to the indicated address. Otherwise, the address register is incremented. Checking the next condition. Okay. So this implementation can be done using multiplexer. What do you mean multiplexer? Can anyone give the answer? What is a multiplexer? Is my anyone in the chat box? I'm waiting for an answer. What is a multiplexer? Data selector. Yes. So how many number of input in your multiplexer are there? 2 power n. Yes. So in that one, n are, what do you mean by n? N is nothing but your number of selection lines. So the output will be your only one, right? Okay. So 2 power n input lines, selection lines are n, output line is only one. So the multiplexer operation is many inputs, single output. So depending upon the selection lines, so one output line will be selected. Okay. Suppose we have 8 status bit conditions, 0 to 7. So 0 to 7 means it will be equal to 8. If we have 8 status bit conditions in the system, nothing but 2 power 3 status bit conditions. So the selection line should be 3. Okay. So the 3 bits in the micro instruction are used to specify any one of the 8 status bit conditions. Yes or no? 0 to 7 according to 000 will get the first status condition. Like that it continues to 7th one, 8th one. Okay. If the selected status bit is in the one state, if the selected status bit is one state, the output of the multiplexer is 1. If the selected status bit is one state, nothing but if it is true, the output is 1, otherwise 0. So multiplexer 1 output means it generates a control signal. It generates a control signal to transfer the branch address from the micro instruction. One output in the multiplexer generates the control signal to transfer the branch address from the micro instruction into the control address register. Yes, ma, all of you, please on the audio, please, and mute it. Don't unmute. Okay. So one output of the multiplexer means it generates control signal. It gives the control signal to transfer the branch address from the micro instruction into the control address register. Zero output means it causes the address register to be incremented to check the next condition. Understood this conditional branching, ma? Understood? So for unconditional branch, the status bit will always be equal to only 1. So for conditional branching, the examples are jump if equal, jump if not equal, jump if 0, jump if not 0. Unconditional branch example is directly jump, only jump. The unconditional branch micro instruction can be implemented by loading the branch address from control memory into the control address register. Okay, understood this conditional branching, ma? So this conditional branching, the hardware whatever we are going to use, conditional branching should be capable of sequencing the micro instructions, okay, within one routine, as well as they can be branched from one routine to another. Is my understanding or not? Until now it is fine. Is my any answer? No answer? Understanding or not? Shall I continue? Yes, ma. Some people are listening without audio, ma. Please make your audio on and mute it. Don't unmute. please. Okay, those who are listening with without audio, they will be put absent. Please make your audio on and mute it. Okay. Next one is the mapping of instruction. So mapping of instruction, nothing but you should map the instruction. Nothing but mapping means, first of all, you need to map the address. Then in address, what instruction has been there that you need to execute. So mapping means you need to map the instruction. So the mapping process, nothing but the transformation or the transformation from instruction code bits to address in control memory where routine is located. Nothing but transformation from your instruction code bits. See here, there might be some instructions whose code bits are already there. Okay, so for that code bits, you need to convert that code bits into an address, okay, where your routine is being located. That is nothing but the mapping process. Okay. Now assume that, for example, we can see, assume that micro instruction specifies to a branch to the first word of control memory. For an example, my micro instruction specifies to a branch to the first word of control memory. In this first word, a routine is located for the given instruction. So see here, we have given as three different instructions are given here. So one is add, second one is and, third one is load. So these three are the instructions that we have seen. Corresponding opcodes are there. These are the instruction codes or opcodes you can call. Okay, so how this code bits or the instruction bits is being converted to an address is nothing but the mapping process. Okay, suppose for an example, I am taking computer instruction as some add one is 4 zeros. Okay, so as we have in opcode, we have 4 bits, so it can specify 2 power 4, nothing but 16 instructions. This 4, as we have in opcode only 4 bits, so during 0 to 16, any number of instructions will be there. Okay, so you can perform with these 4 bits of opcode maximum number of 16 instructions. Assume that the sorry, assume that the capacity of control memory is 128 words. Assume that the capacity of control memory is 128 words. So 128 means it is 2 power 7. Yes or no? 2 power 7 is equal to 128. So we can call 7 bits per word. Okay. So 4 bit of code. If a capacity of a control memory is 128 words, then we require 7 bit address. Okay. How will you mapping? See here. In this form, so as it is 7, we are writing 1 small. Wait for a while. Now it is clear, ma? Now it is clear. Okay, right. So as we have seen, we have 4 bits. Okay, I will go slow. Okay, right. For example, we are taking add. In this one, we will be having 4 bits. Okay, so 4 bits of opcode. So we'll be having 2 power 4, 16 maximum instructions. Hello, sir, still lagging. Hello, hello. Usman, now it is fine. Okay, mapping is converting a 4-bit opcode to 7-bit address. So for an example, we have opcode for and, add, and load. Okay, for an example, if we have 4 zeros, the opcode will return in the this one still some students are not there. Please on your volume, on your audio, and mute it. Now it is clear. Lagging. Now it is clear, ma. Still lagging. 4 up to 1 address mapping process. Fine. Esma, now voice is clear. Okay, shall I move forward? Okay, so mapping of instruction, right? So mapping a 4-bit instruction code into an address, 7-bit address. If it is a 128, capacity of your control memory is 128, then it is 2 power 7, so it will be 7-bit address. Example, we have 3 opcodes, add and load. These 3 are instructions I have taken for an example. So for corresponding opcodes are 4 zeros, 0001, 0010. Okay, so how will you do this mapping bits? So the first MSB bit will be like that. In middle, the 4 bits will be the opcode, whatever the corresponding instruction is there. That will be stored same as your opcode. Okay, so as we need to convert this 4-bit opcode into a 7-bit address. Okay, so as your address format is, instruction format is, first will be your condition 1 or signed 1 or carry 1. Then the next one is opcode. The next one is opcode. And the after that one, that will be an address. Yes or no? So depending on that only, we are writing the 7-bit address as the MSB bit will be stored as 0, then followed by your the corresponding opcode, then again zeros. Okay, it is a 7-bit address converted from your 4-bit opcode. That is nothing but mapping. Understood this mapping, ma? Understood this mapping of instruction? Shall I move forward? Shall I move forward? Okay. Again explain. See, mapping of instruction is nothing but mapping a 4-bit, whatever 4-bit or 5-bit, mapping a opcode or instruction code into a address of control memory. That is nothing but a mapping process. Transformation of instruction code into a address of the control memory. Okay. So here for an example, I am taking as a 4-bit opcode. So we need to convert into a 7-bit address. Why 7-bit address means, as we are assuming the capacity of a control memory is 128 words. So 2 power 7 is 128. So the 7-bit address we are implementing. Okay. For an example, we are taking add and load. So the corresponding opcodes are 4 zeros, and are 0001, load is 0010. So how will you map means, in middle, whatever the x are there, that are the opcodes directly written. Okay, as left to this one, opcode will be your MSB bit will be stored with only 10, as this is your condition or sign or mode bit. On the LSB side, it will be placed the remaining 2 bits, nothing but we are placing as zeros. Okay, so like this, your add 4 zeros will be in the address of 7 zeros. For AND, 4 zeros, 100. For load, 000, 100. Okay, so this is the mapping of a instruction. It is fine, ma? It is fine. Okay. Now we are going for the next one, address sequencing. What is this address sequencing, ma? The micro program stored in the memory, okay, will be in a sequence. So you need to get the address in sequence only. Okay. So as micro instructions are stored in control memory in groups which are specified as routine. Okay. So each computer instruction has its own microprogram routine in control memory to generate the micro operations. Yes or no, ma? Okay. The hardware that controls the address sequencing of the control memory must be capable of sequencing the micro instruction within a routine and be able to and also be able to branch from one routine to another. Okay, so for this one, for every instruction there are four micro operations to be performed. First one is fetching the instruction from memory. Second one is calculating the effective address. Third one is executing the instruction. Fourth one is fetching the returning back to your next address, next instruction. Yes or no, ma? So in this one only, so we will be having four different steps for this address sequencing. So first step is fetching the instruction from memory. So initially, whenever your computer is on, okay, an initial address is loaded into the control address register. An initial address or some starting address will be loaded into the control address register. That address is usually the address of the first micro instruction that activates the instruction fetch routine. The fetch routine may be sequenced by incrementing the control address register through the rest of the micro instruction. Sima, whenever you are on the computer, an initial address will be stored into your control address register. That address will be the address of the first micro instruction that activates the fetch routine. Nothing but takes the instruction from the memory. Okay. Then you need to increment the control address register. Okay, for taking the next instruction. Yes or no? So that is, so after this fetch routine, the instruction where it will be stored, it will be stored in your instruction register in the CPU. First part done, fetching the instruction from memory. Second one. Second one is calculating effective address. Calculate the control memory next must go through the routine that determines the effective address. The effective address calculation routine in control memory can be reached through a branch micro instruction, as we have seen the conditional branching. Okay, so using this conditional branching, you will be having certain specific bits, okay, which goes to your branch where my condition is there. Okay, it will check whether it is met, otherwise leave, otherwise go for the next instruction. So after this, calculating the effective address, the address will be stored in the memory address register. Third one is executing the instruction. So the executing the instruction, nothing but, so the instruction should be executed. So where my instructions are? Okay, the here the mapping process comes into existence. We have an instruction, for that there will be some opcode or instruction code. So the mapping will convert that instruction code into the address. So if you know the address in your control memory, you can take that instruction and execute it. And the fourth one is return call. Nothing but you need to go again to your fetch process, again to your next address, again to your next micro instruction. So for that one, we'll be having a subroutine call and return. Okay, the return addresses where it will be stored. The return addresses can't be stored in the control memory because control memory is only read-only memory. So we'll be having a separate register to store this control address, to store this subroutine, to store this return addresses. That is called as subroutine register. Okay. So the addressing sequencing capabilities required in the control unit are: first one is incrementing the CAR, second one is unconditional or conditional branch depending on the status bit conditions, third one is mapping from bits of instruction to address from control memory, and the fourth one is facility for subroutine call and return. So these are the four instructions which are to be executed for a single instruction to be executed. Okay, now how to find out the address of an instruction code? So this is the block diagram which may be known as to how to find out the address from your control address register. Okay, so here you can see the control memory. The control memory consists of some bits, okay, which determines the addresses, or which determines the instructions. Okay, so some bits are for activating the micro operations to be executed, for a single instruction to be for a single instruction to be executable, and some other bits are being used for specifying the method to get the next address. Okay, so here you can see we have a multiplexer which are having four different options, four different methods. Okay, so the first method is incrementer, incrementing the content of control address register by 1, which will be given as one input of your multiplexer. So after incrementing, the multiplexer selects this one and give it to your control address register. If that address is present, it will be stored in your control memory. Whatever the instruction is being there, that will be executed by the help of micro operations for the corresponding micro instruction. Second one is the branch address. Okay, so branch address and the status bit. How will you get branch address? Branching is achieved by specifying the branching is achieved by specifying the branch address in one of the fields of the micro instruction. In one of the fields of the micro instruction, from that one we'll be getting your branch address. So that branch address will be selected in the multiplexer, and if that address will be given to your control address register, which stores the address, and from control memory it takes the micro instruction and it will be performed. Okay, and using this branch logic, there will be some status bit. So using the status bits, okay, using suppose we have example as 3. So 3 status bits means any one of the 0 to 7 logic. Okay, so it will select the, depending upon the selection lines, one output will be given to your multiplexer. If it is being selected, that address will be stored in your control address register. So the particular address of the corresponding instruction execution, right? And the fourth one, and the third one is, first one is incrementer, second one is using conditional branching, third one is using mapping. Okay, so we'll be having one instruction code using a mapping logic circuit. It will be converted into a 7-bit address. If you have capacity is 128, okay. So the address of 7-bit will be given to your multiplexer, which will select and stores into the control address register, then the same method. So this is the third technique for in your address sequencing. And the fourth one is, so whenever the incrementer is incrementing the control register, okay, there might be cases for getting your subroutines. So the return call address will be stored in this one subroutine register. So the return call address will be again given to your multiplexer. If it is being selected depending upon the selection lines, okay, the address will be stored into this one, taken from the instruction from control memory, and it will be executed. So like this, the address, we can find out the which address in sequence it will be. Is my understanding, ma? Understood until now? I will stop here. Any doubts? Any doubts? Yeah, multiplexer gives only one output. I am telling the 4 techniques which can be implemented for finding out the address. Okay, 4 possible things. Yes, separately. So depending upon our micro instruction or our micro program, okay, so it will take whatever it requires. Suppose if you have some conditional micro program, then it will take some branching one. Okay, if you have directly opcode, mapping logic. If you want to increment directly, it will unconditional, it will take directly increment. Okay, like that. Still any more doubts? Still any more doubts, ma? Are you clear with today's topic? This is very easy if you understand properly. Yes, ma, this is essay type question, ma. Is all of you clear? If you are clear, please tell me in the chat box. We will start the quiz. Shall we start the quiz? Yes, ma. So many people still are with audio not on. So I guess they are not listening. So will you put the absent? And we have noticed that still so many people are using or copying the quiz. So please don't do like that. If anybody found, they are putting a absent without any notice, right? Okay, so we are going to start our quiz, right? Thank you.